This lecture is composed of three main parts. The first section is about the deterioration of metal artifacts in storage environments. I will first give you a brief explanation of corrosion phenomena of metals under atmospheric environments. Then, I will explain the deterioration mechanism of iron and bronze artifacts under storage environments. In the next section, you will be shown experimental results of the impact of humidity on the corrosion of iron artifacts. It is important to think what kind of environment metal artifacts should be preserved in based on these results. In the last section, I would like to explain scientific methods that are available to create a suitable storage environment, together with actual measurement data. First, let me explain the conditions under which metals corrode. Corrosion progresses when metals interact with the environment. To be more specific, corrosion is the oxidation-reduction reaction between metals and oxidants, such as oxygen. Water plays the key role in this reaction. The corrosion process of metals progresses only when water is present in addition to oxidants. Conversely, it is necessary to remove water and oxidants, like oxygen, to suppress the corrosion of metals. Next, I will explain atmospheric corrosion. Atmospheric corrosion is a process that occurs when metals are exposed to the atmospheric environment. Deterioration of displayed or stored metal artifacts is caused by atmospheric corrosion. The causes of corrosion are water and oxygen. These are the same causes for corrosion that occur at archaeological sites. A film of water, which we will refer to as the water film hereafter, so thin that it cannot be seen by the naked eye, forms on the surface of metals. Its state and the salts dissolved in that water determine the degree of corrosion. The figure on the left is a diagram of the atmospheric corrosion of metals. It shows the process in which the thickness of the water film changes. The graph on the right corresponds to the diagram on the left and shows the change in the rate of corrosion as the thickness of the water film changes. Corrosion does not occur in an environment where water films do not exist. The rate of corrosion accelerates as the thickness of the water film increases and reaches the maximum speed when the thickness is between 10 and 50 microns. The Evans drop experiment tests a type of atmospheric corrosion, and the thickness of the water film in the test is likely to be that in stage 4, as seen in the graph on the right. For this reason, maintaining an environment in which water films do not form on the surface of metals is essential for preserving metal artifacts. Now, I will explain the deterioration of stored iron artifacts. Shown on the slide is an image of an iron artifact that cracked while it was stored. Some iron artifacts corrode and disintegrate while being displayed or stored, and therefore lose their academic research value. This is an important issue in preserving metal artifacts that is seen all around the world. Once a metal artifact corrodes, like the example shown here, it cannot be restored. Therefore, it is vital that metal artifacts are stored in an environment that prevents deterioration. Many have the false idea that once these artifacts undergo preservation procedures, such as the removal of salt, they will not deteriorate while in storage. This is incorrect. Artifacts that have undergone preservation procedures will deteriorate if placed under adverse storage environments, such as a highly humid environment. Next, I will explain the deterioration mechanism of iron artifacts, similar to the one you saw in the previous slide. On the upper left is a cross-section diagram of an iron artifact. The diagram on the right is a magnified view of a part of that artifact. There are cases where chloride salts, such as iron chloride 2, accumulate in parts of the iron artifact as corrosion products. When such an artifact is placed in a high humidity environment, the iron chloride deliquesces and water films form. So, in chemistry, to deliquesce means that a solid becomes liquid by absorbing moisture from the air. The artifact corrodes due to the formation of water films. In the corrosion process, a kegenite grows and ruins the shape of the artifact. The image on the slide is a microscope photograph of a cross-section of an iron artifact that corroded while in storage. In the area circled on the photo are water films that formed due to the deliquescence of chloride salts in the iron artifact. In the field of conservation science for cultural properties, these water films are called weeping or sweating. These are strong acid solutions that are produced when chloride salts deliquesce. When corroded fragments are observed under a microscope, we can see that orange needles of corrosion products have formed. This orange corrosion product is a kegenite. As explained before, iron artifacts break from the inside due to the stress created when this kegenite forms. Therefore, it can be said that the formation of a kegenite leads to the disintegration of iron artifacts. For this reason, it is possible to determine if iron artifacts have deteriorated while in storage by observing their cross-section and checking for any sweating or a kegenite. Let us summarize what we have learned so far. Some of the metal artifacts contain deliquescent salts, such as iron chloride 2. Such artifacts corrode when stored in a highly humid environment. On the other hand, some artifacts are believed to not contain chloride salts and are likely to be resistant to corrosion that occurs during storage. Whether a stored artifact is prone to corrode can be determined by the presence of a kegenite and sweating. Now we will take a look at the deterioration of bronze artifacts during storage. Corrosion, which occurs on stored bronze artifacts, is called bronze disease, and this problem has been known for a long time. On the slide is a photo of a bronze artifact that has developed bronze disease. In small areas of its surface, there are whitish-green powder corrosion products. Bronze disease progresses starting from these areas. The schematic diagrams on the slide show cross-sections of a bronze artifact that developed bronze disease. There are areas in the bronze artifact where copper chlorides have accumulated as corrosion products, and on those surfaces are corrosion products such as basic copper carbonate and basic copper chloride that have been produced. Like iron artifacts, when such a bronze artifact is placed in a high humidity environment, the copper chloride deliquesces and causes water films to form. The formation of water films promotes further corrosion of the artifact, and more corrosion products, such as basic copper chlorides, are produced. In addition, formation of pitting corrosion causes the metals in the bronze to corrode, and the artifact loses its thickness. The whitish-green corrosion products on the surface of this bronze artifact, shown in the image on the right, are corrosion products such as basic copper chloride that were produced in the process of the development of the bronze disease. At the bottom of the area where basic copper chloride exits, the thinning of the bronze is likely progressing due to bronze disease. Let us summarize the deterioration of bronze artifacts during storage. 1. There are some bronze artifacts which chloride salts have accumulated inside. 2. When such artifacts are placed in a highly humid environment, deliquescence of chloride salts causes corrosion. 3. Such deterioration is called bronze disease and causes the thinning of bronze. Next, we examine the degree of corrosion in iron artifacts in relation to different relative humidities. The graph shows the results obtained from experimental test pieces that simulated corrosion in iron artifacts. The graph shows the relationship between relative humidity, which will be abbreviated as RH on the slides from now on, and rate of corrosion. The horizontal axis is the relative humidity, and the vertical axis is the rate of corrosion. The amount of iron chloride on the artifact that causes corrosion is changed in the experiment. An increase in the rate of corrosion as the relative humidity increased was observed on samples with 100 milligrams per square centimeter of iron chloride. In addition, these samples showed a faster rate of corrosion compared with samples with 1 milligram per square centimeter of iron chloride. Samples with salts are believed to imitate iron artifacts inside which salts have accumulated, and samples without salts imitate sound artifacts that have no accumulated salts inside. Artifacts without accumulated salts tend to have a slow rate of corrosion. However, the rate accelerated with an increase in humidity. In either case, iron artifacts are required to be preserved in an environment with low humidity. From these results, we can see that the corrosion of iron artifacts is particularly noticeable when relative humidity is 56% or higher, and corrosion is likely to become more severe as humidity rises. This is because the relative humidity at which iron chloride 2 deliquesces is about 56%. Because corrosion accelerates, especially when salts deliquesce, it is of vital importance that iron artifacts are preserved at a humidity which does not cause the deliquescence of chloride salts. This figure shows the factors which cause the corrosion of iron artifacts at various relative humidities and the degree of deterioration. This is a simplified graph that shows the deterioration of iron artifacts at various relative humidities. There are 4 points to note on this graph. 1. Corrosion takes on a different dimension at a relative humidity of 56%, which is the humidity at which iron chloride deliquesces. 2. Corrosion progresses rapidly when relative humidity is 56% or higher. 3. Corrosion progresses slowly when relative humidity is below 56%. 4. Corrosion is not seen when relative humidity is between 10 and 20%. The table on the slide shows the relative humidity in air in equilibrium with saturated salt solutions. Salts deliquesce at a humidity higher than the relative humidity provided in this table. For information, the iron chloride we have been looking at deliquesces at a relative humidity of 56% or higher. According to the table, copper chloride will supposedly deliquesce at a relative humidity of 68% or higher at 20 degrees Celsius, and deterioration is likely to progress noticeably at a higher humidity. The fact that the relative humidity at which copper chloride deliquesces is higher than that of iron chloride suggests that bronze artifacts are less likely to deteriorate while in storage than iron artifacts. Let me summarize the results so far. 1. Deterioration of stored iron artifacts is caused by the formation of water films caused by the deliquescence of iron chloride 2. 2. Corrosion is severe at a relative humidity of 56% or higher, which is the humidity at which iron chloride 2 deliquesces, and the rate of corrosion accelerates as humidity increases. 3. Although corrosion is mild in environments with a relative humidity below 56%, there are cases in which a khagonite may slightly form. 4. Deliquescence of chloride salts also causes corrosion in bronze artifacts. Copper chloride 2 deliquesces at a relative humidity of 68%. 5. Environments with a lower relative humidity are desirable for the storage of metal artifacts. Up to now, we have learned the mechanism behind the corrosion of metal artifacts and what sort of storage environment suppresses deterioration. Finally, I would like to explain how we can make a storage environment that can suppress the deterioration of metal artifacts. The previous slides explained that low humidity environments are suitable for storing metal artifacts, and that it is particularly important to maintain a relative humidity that will not cause salts inside the artifacts to deliquesce. In this section, I would like to explain methods of controlling the storage environment using air conditioning, humidity control agents, and the RP system with actual measurement data on the environment. Let us begin with the method of using air conditioning. On the slide is a graph based on data obtained from storage rooms with and without air conditioning. The horizontal axis is the time. The vertical axis on the right is the temperature, and on the left is the relative humidity. Temperature in storage without air conditioning demonstrates variation through the day. Its relative humidity is influenced by the change in temperature and fluctuates. A relative humidity greater than 80% is observed in August, a season with high humidity. On the other hand, both the temperature and humidity in the storage with air conditioning are almost constant. However, even when air conditioning is used, it is difficult to achieve an extremely low relative humidity, and it may cause metal artifacts to deteriorate. Next is the method using humidity control agents. This method is used to control environments inside display cases at museums. Humidity control agents are made of porous materials such as clay, zeolite, and silica gel. These agents mitigate sudden change of humidity inside display cases and maintain a specified relative humidity. As shown in the diagram, when the relative humidity is higher than the specified value, they absorb water vapor in the air. On the other hand, when the relative humidity is lower, they release water vapor and control the humidity. The level of moisture absorption changes depending on the capillary size and specific surface area of the porous material. Lastly, I will briefly introduce you to the RP system. RP agents absorb moisture and oxygen. By using RPA agents, you can create an environment with a relative humidity of 10% or lower and an oxygen concentration of 0.1% or lower. Here is an overview of the RP system. The RP system is a method that controls the environment by enclosing an artifact together with an RP agent inside a gas barrier film called ESCAL. By adding an oxygen indicator, which is a pink tablet, you can check the concentration of oxygen inside. The graph shows the change in relative humidity produced by the methods described so far. It is possible to create a low humidity environment using air conditioning, humidity control agents, and the RP system. The RP system is believed to be particularly effective in creating a storage environment suitable for metal artifacts. It is important to use these methods together to create an environment in which chloride salts do not deliquesce. The impact of these environment control methods on metal artifacts and their operating costs are listed in this table. The impact of deterioration on metal artifacts will likely be significant in an environment with no air conditioning, especially in Japan where humidity is high. Deterioration can be slowed down by controlling the relative humidity with air conditioning, but this is still not enough to suppress it completely. On the other hand, methods like the RP system that uses dehumidifying agents and moisture barrier films are believed to be effective in preserving iron artifacts. Controlling the environment with dehumidifying agents also has the advantage of having a lower running cost than air conditioning. However, even when using dehumidifying agents and moisture barrier films for preservation of the artifacts, it is necessary to replace them regularly every few years. And now for the final summary of this lecture. Iron and bronze artifacts that contain chloride salts tend to be highly susceptible to corrosion caused by humidity. However, not all iron and bronze artifacts contain these compounds that have a strong connection with corrosion. It is vital that both iron and bronze artifacts are stored in a low humidity environment, as iron artifacts corrode rapidly at a relative humidity of 56% or higher, and bronze artifacts at a relative humidity of 68% or higher. It is important to store metal artifacts in a suitable environment that is controlled by methods such as air conditioning, humidity control agents, and the RP system. And this concludes my lecture.